Hello everyone, welcome to my channel. In this video, we will discuss about the fundamental theorem of arithmetic. We'll also do exercise 1.2. So let's get started. We know that every positive integer or natural number other than 1, either prime or composite number. And if a given positive integer is a composite number, it can be written as the product of two of its factors. For example, let's take 625. I can write this 625 as 5 into 1 into 25. 5 and 125 are the factors of 625. And see, these factors can be prime or composite. See here, this is a prime and this is a composite number. Again, we can write this 125 as equal to 5 into 5. This 125 I can write like this. Correct. Again, I got this my prime number. This is also prime number, and we know this 5 is also a prime number, and this is a composite number. Again, I can split this 25 into two factors. So I can write this as 5 into 5 into 5 into 5. So here what we did, if we keep on doing the factorization like this, ultimately we'll arrive at a stage when all the factors are prime numbers. For example, in 625, I have taken first wrote this 625 into its two factors 5 and 25, and again I split this 25 into two factors 5 and 25. Again I can split this 25 into 5 into 5, means till I got all the factors prime numbers, and I can write this as 5 raised to power 4. Let's find out the prime factors of 196. So let's do the prime factorization for this. First, this 196, it will go with 2. So I'll write here 2 and I will get 98. And this 98 will go with 2. And here I will get 49. And this 49 will go with 7 7s are 14. So this is one way of representing this prime factorization, and another way is like this. We can also do like this also, and then again 2, this will become 49 7 7. So we can write the prime factors of 196 as 2 into 2 into 7 into 7. So 2 is our prime factor and this 7 is also a prime factor. So it means we can write this as 2 raised to power 2 into 7 raised to power 2. So we have represented this number 196 into its prime factors 2 and 7. So the fundamental theorem of arithmetic says every positive composite number can be expressed or factorized as the product of primes, and this factorization is unique apart from the order in which the factors occur. Let's see the meaning of the prime factorization of a natural number is unique except for the order of its factors. For that, I'll take one example. The prime factorization of this number 8232 is equal to 2 raised to power 3 into 7 raised to power 3, and this will always be like this. But we can change the order of its factor, means we can write this as 7 raised to power 3 into 2 raised to power 3, or we can write this as 7 raised to power 3 into 2 raised to power 3 into 3. The order doesn't matter, but the prime factorization is always unique. There are two main applications of fundamental theorem of arithmetic. One is to prove the irrationality of irrational number like square root of 2, square root of 3 and square root of 5. And second application of this theorem is to find the decimal expansion of a rational number is terminating or not terminating. do this application in next coming videos, and here we'll see how we can use this the fundamental theorem of arithmetic to find HCF and LCM and problem related to them. And how, let's do exercise 1.2, and which is based on the fundamental theorem of arithmetic. So first question here is express each numbers as the product of their prime factors. So first question here we have 140. Here we'll do the prime factorization for 140. We know 140 is, we can write like this, it will go with 2, this will come 70, and then again 2, this will come 3, 5, and then this will go with 5 into 7, and 7 and 1. So I can write this 140 as 2 into 2 into 5 into 7. So this is equal to 2 square into 5 into 7. So I have written this 140 as the product of its prime factors 2, 5 and 7. So next question we have to find the prime factors of 156. I write 156 here and it will go with 2, 7, 14 and 8. Again it will go with 2, 3, here 6 will come, and 9, 39. So 39, next it will come in, it will go with 3, 1 and 3. So prime factors of 156 are 2 into 2 into 3 into 13. So I can write this as 2 raised to power 2 into 3 into 13. Third question we have 3825. Let's find prime factors of this number. First check the divisibility with 2. It won't go with 2, it will go with 3. 1, 2, 6, 2, 7, 5. Again check the divisibility of this number with 3. Yes, it will go with 3. I'll get 4, 2, 6, 1, 5. Again check. No, it will not go with 3. Now it will go with 5, 8, and this will go with 5. Next again this number will go, 85 will go with 5, 1 and 3, 7. No, the 17 is a prime number, so after that it will not go. So prime factors of 3825s are 3 into 3 into 5 into 5 into 17. I can write this as 3 raised to power 2, 5 raised to power 2 into 17. Try to do these question number 4 and 5th yourself DIY and write your answers in comment box. Here second question we have, find the LCM and HCF following integers and verify that LCM into HCF is equal to product of two numbers. So let's take first question here. First is 26 and 91. Now find the prime factors of 26. We know we can find the factors like this. It will go with 2 and it will become 13. Then 13 will not go. So this I can write as 2 into 13. And 91. 91 we know, 91, the factors of 91 are, it will go with 13. 13 sevens are 91. So its factors are 7 into 13. So let's find LCM. What is LCM? LCM we have to find. So LCM is the greatest power of each prime numbers. So here the greatest, first we'll see 2. Here we have 2, here we don't, we'll write 2 here. And 13, we'll see the greatest power of 13, only 1, so we'll write here. So we left with 7 and we'll write 7 also. And now this will come 13 twos are 26 into 7, and 26 is equal to 182. Now let's find HCF. What is the HCF? HCF is the product of the smallest power of each common prime factor in numbers. So common factor we have to see. So we have only one common factor here, 13. So HCF of these two number is 13. This is my answer. Let's find the multiplication of HCM and HCF. So this will become 182 into 3. If we multiply this, we'll get 2366. 2366. Now let's see the multiplication of numbers 26 and 91. 26 and 91. This will be 6, 2, 4, 5, 19, 8, 23. So this will become this. So same answer I will get. So it means, hence proof, the product of LCM into HCF is equal to product of two numbers, product of 26 and 91. Always remember that LCM of two or more numbers is always equal to the product of the greatest power of each prime number. Okay, and HCF of two or more numbers is equal to product of the smallest power of each common prime factors. Here we have to see the common prime factors and we will take the smallest power of common prime factors. Always remember that HCF is always a factor of LCM. The second question, two numbers are 510 and 92. Do this question yourself and write your answer in comment box. First you have to find the HCF and LCM of these two numbers, and after that you multiply the HCF and LCM of these two numbers and then multiply these two numbers and you'll get your result. So third question. So next question, here we have to find the HCF and LCM of these two numbers 336 and 54. So let's take first 336. Now let's find the factors of 336. We know this is equal to 2, 1, 6 and 8, and after that again 2, 8, 84, 2, it will go with 4 and 2, 2 and 1 will come, and then this will go with 3, 7s are 21 and then 7, 1. So I can write this as, how many 2's I have? 1, 2, 3, 4. 2 raised to power 4 into 3 into 7. So now let's find the factors of 54. So 54 is, factors are 2 2's are 5 and 7, and then 3 9's are 27 and 3 into 3. So I can write this as 2 into 1, 2, 3. 3 raised to power 3. So let's see what is the LCM. The LCM, for LCM we have to see all the factors and we have to take the maximum or greatest power of the factor. For example, this 2 and here 2 raised to power. So I will write here 2 raised to power 4 into. Next we have 3 and 3 raised to power 3. So I will write here 3 raised to power 3 into. Next we have 7 and here we don't have 7. So we will directly write 7. So after doing this, we will get, after multiplying this 2 raised to power 4, I will get 16 into 27 and 7. If I multiply all these things, I will get 3024. So next we have to find HCF. What is the HCF? For HCF we have to see the common factor and smallest power of the common factors. So here see, we have 2 raised to power 4. Here also we have 2. So we'll take the smallest power of 2, which is 2. Again here see, we have 3 and 3 raised to power 3. So smallest power here for this factor is 3. So I'll write here. Here we don't have 7, here we have 7. So it means the smallest power of 7 is 0. We won't write here anything. So this will become equal to 2 into 6, which is 2 into 3, which is equal to 6. Let's multiply LCM and HCF. So 3024 into 6. So after multiplying these two, I'll get this 18,144. Now let's multiply numbers. Means 336 into 54. If I multiply the same thing, 18144. We can say that the product of this HCF and LCM is always equal to the product of numbers, given numbers. So here given numbers are 3 336 and 54. So we have verified our answer. Here third question says find the LCM and HCF following integers by applying prime factorization method. So here first question is this. I'll do this question. We have to find the LCM and HCF of 12, 15 and 21. So first we'll do the prime factor for 12. So let's write the factors of 12. So this is 2, it will go with 2, 6 are this, then 2 3s are this. So I can write this as 2 raised to power 2 multiply by 3. Similarly for 15, the prime factorization if we do, I'll get 3 into 5. And 21, we know 21, 3 into 7. So see, what is the HCF? HCF means we have to find out the common prime factor in these three numbers 12, 15 and 21. So see, the common prime factor here is 3. So the HCF of these three number is 3. Now let's find the LCM of these three number. LCM. What is the LCM? In LCM we have to see the greatest power of all prime numbers. So here C2, we'll write 2 raised to power 2. Then we'll see for 3. The greatest power of 3 in all these 3 is 1, 3 raised to power 1. Then 5 will also come and 7 will also come. So this will become 4 into 3 into 5 into 7. So this will become equal to 12 into 5 into 7. 60 into 7, which is equal to 420. So my LCM is 420 and HCF is 3. So next question we have, find the HCF and LCM of these three numbers 17, 23 and 29. We know all these three numbers are prime. So the HCF of prime numbers will be 1 because we do not have any common factor except 1 in these numbers. So 1 is the HCF of these three numbers and LCM will be the multiplication of these three numbers. And if I multiply these three numbers, I will get, this will become equal to 11339. So last question here we have to find the HCF and LCM of these three numbers 8, 9 and 25. We know prime factorization, if we do the find the factors of 8, we'll get 2 and 2 1 means 2 raised to power 3, and 9 we can write 3 raised to power 2, and 25 we can write this as 2 raised to power 5 raised to power 2. So what is the HCF of these three numbers? We know we don't have any common factor except 1. So 1 is the HCF of these three numbers. And what is the LCM? LCM will be simply the multiplication of these numbers. 2 raised to power 3 into 3 raised to power 2 into 5 raised to power, which is equal to 8 into 9 into 25, which is equal to 1800. So fourth question, here we have given that HCF of these two number 306 and 657 is equal to 9 and find LCM. So for that we'll use this formula. The multiplication of HCF and LCM is always equal to product of two given numbers. So here my numbers are 306 and 657. So HCF is given. So LCM will be equal to, from this formula, 306 multiplied by 657 divided by this HCF. So I'll put the value of HCF. HCF is 9. So this will become equal to 57 divided by 9. So this 3, this will go 1, 0 and 2, and again it will go with 3. We'll get 3 3s are 9, 1, 34. So this will become 34 multiplied by 657. After multiplying these two numbers, I will get 22,338. This is my LCM. Here fifth question we have, check whether 6 raised to power n can end with digit 0 for any natural number. So for these type of questions, you have to remember that if 6 raised to power n for any n ends with digit 0, then it would be divisible by 5. Okay, it means there should be 5 in the prime factorization of 6 raised to power n. So let's see the prime factorization of this. We know the prime factors of 6 are 2 and 3. So we can write this as this 2 raised to power n and 3 raised to power n. So factorization of 6 raised to power n, we do not have any 5. We can say that no, 6 raised to power n can never be end with the digit 0 for any natural number, because we do not have 5 in its prime factorization. So next question, we have explained why this number and this are composite number. So first I will write this 7 into 11 into 13 plus 13. So see here we have plus sign and this is multiplication. So we can take this 13 out and we left with inside we have now 7 into 11 plus 1 into 13. Correct? This will become equal to 77 plus 1 multiply by 13, which is equal to 78 multiply by 13. Now we will find the factors of 78. We know that we can write this number as this 2, 3 and 9. Then it will go with 3, 1 and 3. So here I can write this as 2 into 3 into 13 into 13, means this is equal to 2 into 3 into 3 raised to power 2. See here, for this number we have more than 2 factors. So we can say that's why this number is a composite number. So we can say that because this whole thing has more than 2 factors, that is why this is a composite number. So here see this, here also this 5 is common, so we'll take this out. We can write this as 5 multiply by 7 into 6 into 4 into 3 into 2 into 1 plus 1. So this will become equal to 5 into, this is 42 into 12 into 2 plus 1, which is equal to 5 into 42 into 24 plus 1. Now this will become 5 into this, after multiplying we will get 1008 plus 1. So this will become 5 into 1009. So here also it is a composite number as it has more than 2 factors. So last question of this exercise is, there is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in same direction. After how many minutes will they meet again at the starting point? Now we have to find out after how many minutes they will meet again at the starting point. So they are saying here that we have a circular path. This is my circular path. Suppose the Sonia and Ravi, they have started from this point A. So Sonia is taking 18 minutes to complete this one round, correct? And Ravi is taking 12 minutes to complete this round. So this question we can, let's see, we can write this as 1 into 18 is equal to 18 minutes. Okay, and to complete second circle, she will take 2 into 18, which is equal to 36 minutes. And to complete 3 rounds, 3 into 18, which is equal to 54. Now see for Ravi, this is for Sonia's time. So let's see for Ravi. Ravi is taking 12 minutes to complete one circle. So I can write like this. And 2 means 24 minutes he will take to complete 2 rounds of this circle. And 3 into 12 to complete third round he will take So to complete his third round, he will take 36. So here see, we are getting 36 and here also we are getting 36. It means they will meet again at 36 minutes. So we can simply, if we take the LCM of 18 and 12, we'll get 36. So for these type of question, we'll take LCM. So we can say the time taken by both to meet again is equal to LCM of 18 and 12. So let's find the LCM of 18 and first we'll do the factorization of 18, prime factorization. 2, 9, 3 and 3. This is equal to 2 into 3 raised to power 2. And for 12 we can write like 12, 2, 6, 2, 3. 2 raised to power 2 and 3. So the LCM of 18 and 12 is equal to, what we have to see? We have to see the common factor and we have to take the highest power of the common factors. So here see, this 2 and here also 2. The highest power is 2 raised to power 2. So we'll write here. So here we have 3 and 3. So we'll take the highest power of 3, which is equal to this, which is equal to 4 into 9. Which is equal to 36. So it means they will meet again at 36 minutes. Okay, from here also we got 36 and here also we got. So 36 means the Sonia will complete his second round and Ravi will complete its third round. So with this we have completed the fundamental theorem of arithmetic and exercise 1.2. Thank you everyone for watching my video.